Hi, everybody. How you guys doing today? Awesome. So the name of the talk today is Building Reliable Lakehouses with Apache Pulsar and Delta Lake. My name is Nick Karpov. I'm a developer advocate at Databricks. I've been part of the Databricks team for 5 years. I've worked as a customer success engineer and a solutions architect, and I actually recently joined Databricks again as a developer advocate. During my time at Databricks, I've worked on a lot of Delta Lake use cases, Lakehouse use cases, data warehousing use cases, so I'm excited to be here today and talk to you. All right, so today we're going to talk about basically just 3 things. We only have 25 plus 5 for questions, so we're going to stick to this, and hopefully it's enough to get everybody started for those of you who aren't familiar with Delta Lake and everything that it has to do with. So the first piece is just a little bit about the Lakehouse architecture in general. I'm going to talk about data warehousing, data lakes, and Lakehouse, and the progression from one to the other. Then I'm going to talk about Delta Lake. Specifically, we just released Delta Lake 2.0. It's a very exciting release for us, so I'm just going to talk about a few of the features that are part of it. And then finally, Delta Standalone, which is our connector, and that connector is what allows other connectors to work with Delta Lake. So it's a standalone JVM library that you integrate with, and then you can connect to Databricks, or to Delta Lake, sorry. That'll kind of naturally fall into the ecosystem. I'm going to talk a little bit about the Pulsar connector, the Pulsar IO Lakehouse connector, the Delta source and sink, and kind of a few comments on that because I've been playing around with it lately, and that'll be it. So let's get started. All right, the Lakehouse, a very brief history. So it all starts with data warehouses. They've been around for a very long time, I'm sure you all know. And they've been around long enough that they're now a staple of every enterprise organization basically on the planet. So it's just, it's a purpose-built data warehouse for external data stores and operational data stores to feed into. And that provides a central location for reporting, for BI, for analytics, all kinds of use cases. But the problem with data warehouses is that they've been around for a long time. So there's a lot of gaps. Now, those gaps roughly fall into 4 categories. The first gap is in data. Traditionally, these are relational data warehouses, so they only support really 2-dimensional regular tabular data with schemas. That worked for a very long time and continues to work very well, but there's poor support for raw data, images, video, audio, anything you might need to do kind of in the modern world with all the new data streams that are available. The second is usability. So SQL is extraordinarily flexible, no doubt, but the modern data science and machine learning kind of ecosystem grew up in a fairly imperative and programmatic environment. So what that means really is that there's always been this gap between the SQL world and the data science and machine learning world. So data warehouses have consistently struggled with that. The third is interoperability. Data warehouses classically require lift and shift to basically get anything done anywhere else, right? You got to lift and shift to get stuff in, you got to lift and shift to get stuff out. It's expensive, it's difficult to maintain, it's difficult to develop, ETL jobs are all over the place, on and on. I'm sure you guys have had experience with that. The last is scalability. Kind of at the beginning, I would say that fundamentally, data warehouses had scale limits just in principle. As they move to the cloud, some of that's been addressed, of course, but at great cost. It's very expensive to run these things. They're just incredibly expensive, and that's all there is to it. And that kind of brings us to data lakes. So in the past 10 to 15 years, data lakes, or I'm sure some of you have heard data swamps, have kind of awkwardly stumbled into addressing some of the concerns and those gaps that I mentioned in data warehouses. 2 of those things I would say are data. So we've dropped the constraints of schemas, so you can put pretty much anything you want in a data lake. And the second one is scalability, right? You can't really run out of storage, and if you do, add another server, it's just commodity hardware. Or if you're on a cloud object store, it's kind of not your problem. It's fairly cheap these days. So those 2 things are great, but they didn't address, and rather made more complex, the other pieces, right? So now we've dropped our stuff in the data lake, and we have no way to really get it out without doing a lot of work. We've lost schemas, enforcements, governing, basically everything the data warehouse did for you, you lost. And now you have just all this data lying around, and you can't really access it. Finally, it's poor performance because when you do want to go and access it, you have to suddenly go read it, figure out what it is, then enforce a schema on read, and then you can do something with it. So the reality is that these two things actually coexist together. We have data warehousing on the left and data lakes on the right. And this is what most organizations look like today. I'm sure you guys are in organizations that look like that today. And even Databricks is like that today. And the problem with this is that we've tried to address the problem with data warehouses with data lakes, and we've ended up making everything more complex. We've tried to get the best of both worlds, and actually what we have is the worst of both worlds. So that brings us to kind of the innovations that we worked with over the last several years to create what we consider kind of the right way to do things, which is the Lakehouse Architecture. Now, the idea behind a Lakehouse Architecture is actually very straightforward. It starts with a data lake at the bottom. So this is just your normal cloud object store, HDFS, whatever it might be. On top of that, and this is the key point, is, well, in this slide it's Delta Lake, but there's other technologies, Apache Hudi, Iceberg, and that's really the transactional layer, right? The metadata layer that sits on top of the data lake. And that's the layer that provides you schema guarantees, enforceability, ACLs, and things like that. On top of that layer are the engines. Now, of course, Pulsar, Spark, Flink, on and on and on. And the idea is that these things are completely decoupled so that you can support whatever engine you want. So in the data warehousing world, where you had to lift and shift to take advantage of the latest and greatest, for instance, Snowflake. Snowflake's great. You got to put all your stuff in there. You can't really bring your own engine. So if there's something somebody else is doing better, you're kind of stuck. In this architecture, you can bring your own engine, whatever it might be. So if you're innovating and creating your own things or using new products, it's pretty straightforward. And finally, what all that does, the ability to separate the storage from the metadata, from the engine, and finally the use cases, it actually opens them all up. You don't have to lift and shift and do things in different places. Using one single layer in an engine of your choice, you can actually do streaming, you can do regular analytics, machine learning, whatever it might be. All in one place, your data stays open, free, on the data lake, just as it always has. You don't have to make multiple copies, ETL jobs, on and on and on. So that's kind of the journey to the Lakehouse architecture. Now, as part of the previous slide, you saw that I had Delta Lake in the middle, and that's kind of your open source storage format layer, right? And that's exactly what Delta is. It's an open source storage format layer, and it provides ACID transactionality on top of data lakes, which is kind of the key component of a database. And honestly, it's the key ingredient to these data lakes, or to taking a data lake and turning it into a real lake house. Right? And so there's other technologies like Hudi and Iceberg that I mentioned, and Delta Lake is one of them. Now, that metadata layer is not just like Hive Metastore or other metastores, right? The key to that transactional layer is that it's scalable and it lives on disk or on the cloud storage together with your actual data. So it doesn't need to move around. You don't need additional services. All you need to do is implement the protocol, right? So just a set of rules, how to read and write from this thing, and you're off to the races, right? There's no need for separate services. Now, a little bit more about Delta. We actually presented Delta last year, and maybe some of you were at Data and I Summit a couple months ago, so I won't go into the gory details of Delta. I'll just mention 3 important things. The first is our new release, and the other 2 things are 2 features that I think address very much kind of the Lakehouse principles and some of the problems with data lakes, right? So the first thing is as of June 2022, just a few months ago at Data and AI Summit, we announced that Delta Lake is now fully open source. So in the past, in the history of Delta Lake is that it was developed at Databricks. It was a proprietary technology, but now it's fully open source. All the core features are open source, including Z-ordering, change data feed, anything you might want, is fully open to the community and available as part of the Delta 2.0 release. And the other 2 things are these 2 features, data skipping and clustering, Z-ordering, and the change data feed. And I'm going to talk a little bit about those 2 features specifically because, like I said, they relate to enabling lakehouses very much so. And also, sorry, if you want to obviously find out more, you can see the full release note details on GitHub. So, data skipping and clustering. It begins with collecting statistics, really, right? So, Traditionally, when you write files to cloud object stores with normal engines, at least in the past, you just dump these files out. And like I said, you have no schema, you don't really know what's going on, and you're certainly not collecting any additional information that might help you filter it later. Now, developers can certainly do that themselves, but there's no need to recreate the wheel. So one of the new things in Delta Lake 2.0 is column statistics. So what happens is actually very straightforward. Every time a write is performed with some piece of data, for the fields in that data, we collect summary statistics, so minimum and maximum. Obviously, it can be extended to more, but for now, it's just minimum and maximum. And what that allows you to do is that when you go back to read that data, right, the protocol, assuming you implement it correctly, allows you to essentially filter data that you don't need. So actually, you can see on this slide, on the right-hand side, I have a query, a relation, some predicates, and the 3 files that make up that relation. So the relation is events, the 3 files are Parquet files on disk, and the statistics that you see on the right, min, max for each field, are the statistics that were written to the Delta log. So when we actually submit this query to this relation events with the predicates 2020 for year and 24,000 for unique ID, the first file can be eliminated because the year 2020 does not belong in the range 2018 and 2019. So that file's gone. And the second file only has IDs between 12,000 and 14,000. And since the predicate is and, we need both conditions. The unique ID cancels that out, and we only have 1 file left to read to find our data. So that's 66%, all gone, just because of this small little piece of collecting statistics. The one last note is, of course, Parquet has row group filtering and some advanced features that allow you to read less, but you still have to read, right? When you do this metadata operation, you read just the statistics for the entire table all at once, so you don't actually have to go to the separate files and read them just to find out that you didn't need to read them in the first place. Now, the statistics collection is neat, but it also suffers from its own set of problems, or rather, it's not good enough. And what that means that it's not good enough, actually I'll go back to the other slide, is in file 1 and file 2, if you look closely, you can actually see that the year has an overlap, right? So 2018 is available in both file 1 and file 2. So what that means is we have an intersection between the statistics. Now, z-ordering is just a fancy spatial curve thing, algorithm, that allows us to minimize that intersection, right? So if you can imagine 2 files with 2 ranges of the values that it holds, right? As they cross over, the more they cross over, the worse it is, because we have to look at both files. The less they cross over, the less likely that we have to look at both files. Ultimately, we'd like to look at only 1 file. So kind of the ultimate instance of this, of ordering your data is that it all has exclusive ranges, right? So z-ordering is a way to achieve that, and just briefly, on the left-hand side, you actually see 2 of the same tables. They're just slightly different ordered, right? So it's the same data, the same number of files, and it's the same relation. But on the left-hand side, you have just regular ordering with some statistics. And to find where x is 2 or y equals 3, you have to check in 2 directions, 2 orders, and that leads to 9 files scanned. But when you z-order that data, which means basically you cluster x and y's together, you reduce your scan space by 2 files, and now you only have to scan 7 files. Now, z-order isn't the only spatial curve. There's Hilbert curves, KD trees. There's a few other things that can be done. For now, z-order is the thing that has been open source, and it provides kind of a framework for implementing other spatial curves within Delta. One of the last key benefits, of course, is that you can evolve these things, right? So different partitions, different parts of your data can have different z-orders, right? So if your query pattern on some partitions is a certain way, and your query partitions on another partition are a different way, you can z-order on different fields and different partitions. So it's extraordinarily useful. And if your data evolves, then you can also just update it, right? So if your query patterns evolve and somebody's searching for something else, or you've added new fields, just z-order your data, re-optimize it, and enable those fast reads. So that kind of covers performance. And those are the kinds of techniques that a transactional layer or a metadata layer in between the cloud object stores and the engines provides. Now, the other feature is less about performance and more about interoperability. So in some engines and data formats, this actually comes native, but Delta was originally a copy-on-write method of doing things. And so as part of that, what that meant is that we would always just rewrite the files, right? We wouldn't merge it later, right? So if you changed a file, it changed in place, and you kind of lost anything that happened in between, right? So what that meant is that it made pretty difficult to tell what changed. And change data capture, common pattern in all of data, is super important. And so change data feed in Delta has introduced that ability to Delta. Right? So now we can get row-level changes to whatever happened to your table are available. So let's take a look at a quick example so you can see what usually causes these things. So you can see that on the left we have file 1, and on the right we have file 2. To get from file 1 to file 2, there was a merge or an update or a delete. Something happened, right? We changed a bunch of rows. And like I said, because it's merge is copy on write, we simply just we write a new file, we tombstone the old file, it doesn't matter anymore. And of course, so you get fast reads, but you don't see what happened to the rows, right? To actually see what happened to the rows, you have to do a join between versions or files. It's a complicated process. It's error prone. Everybody has to redo it themselves. And of course, you don't actually know, for instance, what's delete, what's an insert, what's an update. You can figure it out, but it's difficult. And it's expensive. For instance, this example shows that I have to join the two files. And actually, if you do a merge, you're performing a join already. So you were in a position to do something about it, but you didn't. And so now you got to go back and do it again. So that kind of sucks. So the change data feed feature, which is live in Delta Lake 2.0, basically implements this thing. It does it. So as part of going from file 1 to file 2 in between versions, when you some kind of DML operation, an update, delete, merge, we actually write out the change files with the new version, right? So what that means is that it becomes super simple to read those change data feeds in the future. So now you can create these incremental pipelines. And this is just an example. For instance, there's a streaming API, so you can read these changes in a stream. There's a batch API if you want to view like a certain change data set for a certain date range or version range. All these things are available. And as actually, last night we cut a 2.1 release. This is 2.0, but last night we cut 2.1 release. And so where it says SQL support in the future, that's no longer true, at least from the Spark connector side. As part of Spark 3.3, together with Delta Lake 2.1, full SQL support is also in there. Awesome. So those are those two features that I wanted to highlight. Of course, the Z ordering and data layout things that exist in Delta Lake are super useful for performance. And the change data feed is incredibly useful for interoperability, really. You can take and read that change stream, put it somewhere else, utilize it somewhere else in real-time applications, whatever it might be. So it kind of speaks to the Lakehouse principles of keeping things open, allowing interoperability, and of course, performance. And that kind of leads us just to this slide about the ecosystem at large. So we've already implemented a lot of connectors in the past year, and actually most recently, Flink, Trino, and Presto. And the Pulsar connector, because this is a Pulsar conference, of course, is still in development, but there is a GitHub repository, and it is available. So I'll talk about that in a second. Before I jump into the Pulsar aspect, I will say one more thing about Delta standalone. Now, Delta, when I say, oh, it's open source, this big project 2.0, what I'm actually talking about is the Delta Spark connector, right? Because Delta is a protocol, it's a way of doing things, right? It's not, you can't close it, it's open, because it's just a set of rules. And so the Delta project is the Spark connector for Delta. Now, those two things are highly married because Databricks was originally a Spark company, and that's just how things panned out. So as part of the progression of making Delta open and interoperable with everything else, we also released a Delta standalone project. Now, the Delta standalone project is just a separate JVM Java-based library that you can use to read and write from Delta. Right? It has no dependencies or very low dependencies, no dependency on Spark, certainly. And it's actually the basis of all these connectors, including Pulsar. We just recently released 0.5 of this standalone connector, and you should definitely go take a look at it if you're interested in integrating and connecting with Delta in a non-Spark fashion. And that brings us to the Lakehouse connector for Pulsar. Now, it's still under active development by some of the Stream Native folks, and I actually spent a few weeks playing around with it, and it's really cool. And I just wanted to highlight a few of the things that it supports and a few of the things that it doesn't yet support. So the first thing is that it supports Delta Lake as both a source and a sink. I actually just realized I have those arrows upside down, at least on one side. So it's meant to be a circle. There's a demo available on the GitHub page. You can run it. If you just go to the GitHub, pull that, and run the demo. It's really cool, but there is one caveat, at least today, and that's kind of what I hope to solicit from everybody here, is some help and some contribution from those who want to integrate Delta Lake with Pulsar. So currently, this demo actually demonstrates Delta to Pulsar to Delta, so a round trip. It reads from a Delta source, pushes into Pulsar, and then Pulsar syncs it back into a Delta sync. Currently, it works very well for append-only use cases, right? So that source Delta table, if some external system like Spark or something else or Flink is changing it, everything works as long as those changes are append-only. Today, if you make a change that's actually an update, delete, or a merge, which is potentially both, it actually feeds those changes and it doesn't recognize that there's something different about them. So that's just something to call out and something that we hope to change very, very soon. And then finally, I did mention change data feed feature today, and it's fairly new to Databricks. Like I said, or Delta, sorry, it was open sourced just in June. And the CDC files that it actually writes out in the change data folder, like I showed earlier, it's not implemented yet in the Pulsar connector. So the Pulsar connector only recognizes add files and remove files. So if you add something or you mark a file as old and it's removed, Pulsar recognizes those, but it doesn't recognize the change feed files. And that's very useful because those change feed files are much, much better. They're much smaller. You don't actually have to add everything and delete everything, add everything and delete everything in order to get your changes, right? It's just the actual changes, the actual rows that changed. And so that kind of leads us to the last little bit. So the Delta community and the past year of growth. Just a nice slide to show that we've experienced tremendous growth since it was first open sourced last May, as Delta 1.0 was released. We've added a whole host of connectors in that time, and Delta's increased to 7 million downloads a month. This is actually as of May, so I'm sure that the numbers are even better now. So just a little peek into kind of the growth that Delta's experiencing. We have, I believe over 70 organizations that have contributed to the project so far. So we're really excited about that. I think almost 200 contributors. I don't know if the numbers are yet up to date. So there's tremendous community contribution to this thing. And that's very exciting. And we'd like Pulsar to kind of get that to completion and bring it all together. So with that being said, these are just some additional links: the GitHub, Slack, Twitter, of course our main page. So I hope you guys enjoyed the talk today, and we look forward to hearing from you and any contributions you'd like to make. So if you'd like to get involved, please reach out to me and or come speak to me after the session. So thank you.